in session 3, we're going to talk about how to perform a GWAS using the PLINK software. So we've discussed how and how to do an association analysis. Question?
It looks like the files that are on the bottom of the course website are the same that are passed in the file link script.
Say it again.
The files in the memory stick, are they also on the website?
Some of them are, yeah. So the large PLINK files, the largest PLINK file, which is like almost 300 megabases, is not. Yeah, so there's going to be some overlap as well, yeah. So you can choose to download the ones that you haven't downloaded our web as well. So I put some of the PLINK files on the website that were smaller ones, but the huge PLINK file that's transferrin.bim or bed is pretty huge. So that you could download. But if you already have the other files already from the website, then you don't have to download that again. Okay, so we're going to talk about the PLINK software. This is a very useful tool if you're going to be doing genome-wide association studies for large-scale data. So we've done we're testing one SNP or a few SNPs for association analysis, but when you have these large data sets with thousands of individuals and hundreds of thousands, even millions of SNPs, using R can be quite slow because you have to read in all this data into memory and trying to analyze it. So PLINK is a nice software tool for analyzing large-scale analysis in a computationally efficient manner. So they've developed some nice code to read in data pretty fast and run the analysis. And you'll see that with the PLINK software, using your laptop, you're going to be able to do a genome-wide association study with over 1,000 individuals and 100,000 SNPs in a matter of minutes, which is actually quite impressive. All right. So the website, and there's a link to it on the course website. The website for PLINK is here, and so this is the main website that you'll be accessing if you have any questions about how to run things. So it's an updated website. They do a really good job. And so here's the PLINK website. So all the information that you need is online. So they update it pretty often. The last update was 15th of May. There's a new version of PLINK available. So just any information that you need about the PLINK software, what are the commands, how to use them, examples, you can consult this website. Okay, so they update it quite regularly. Okay, so there's a lot of features available with PLINK. So the number of data management tools. So one nice thing about PLINK is that it's a nice tool set for reading in data in a variety of formats. Okay, so recoding or reordering files. So merging 2 or more files. So let's say you have data from 2 different collaborators. You want to merge it. PLINK has a number of ways to kind of merge files as well. So for example, if you want to extract subsets of SNPs or individuals and create a file, you can easily do that with this. Flip strands of SNPs. So often, case for example, if you have a collaborator, you want to do some type of meta-analysis or combine analysis across studies. Some studies are going to be genotyped on different platforms. Okay, and so different platforms, and so different platforms, even if they have the same SNP that's been typed, one may have typed one strand, another platform may have typed another strand. So how do you do that in an efficient manner to kind of flip so that the A's match the A's? And so one might say A, one have genotype the other strand. So you could do that easily by flipping strands with PLINK. Okay. And also what's nice is that you can compress the data in a binary format. So these data sets get really, really large. And so you often want to compress it, and you can do that easily. As you'll see an example, it can give you quality control statistics per SNP or per individual very fast. So if you want to calculate Hardy-Weinberg equilibrium at all of your SNPs and choose some type of threshold to determine which ones you're going to accept or reject or include in your analysis, you can easily do that. You might want to include individuals who have high missing genotypes. Maybe the sample was of bad quality. You can easily do that as well and calculate missing genotypes. If you're interested in estimating relatedness among individuals, they have statistics for that. For example, you have a sample, you don't know who's related to who, but you want to estimate it from the genome screen data, you can at least easily do that. So there's some issues with it if it assumes that individuals are homogeneous, and if individuals are not homogeneous or not from the same population, then it can give you bias estimates. And so there's a lot of software for that. You might want, if you have family data, you can easily check for non-Mendelian transmission, which is often used as quality control features to determine which SNPs may be bad, where you're seeing certain alleles in the parents, but you don't see it in the children, so you know there's a Mendelian error. Okay, so that's probably a bad SNP, a bad cause, something's wrong, bad quality, so that you can flag that. So there's a bunch of things. So for association testing, which is what we're going to be doing, you can do a case control association testing. We talked about Fisher's exact test. We talked about the Armitage's trend test. We talked about dominance testing in general models. So you can do that. You can do all of that in PLINK. So everything that we've done in R, you can also easily do that in PLINK with a simple command line option. Okay. So somebody mentioned about having data on family. So it can do family-based association tests, TDT, CIPSA tests. You can do quantitative trait association testing as well. Association testing conditional on one or more SNPs, which is commonly done. So for example, let's say you found a SNP that you know is genome-wide significant, but you want to test all the other SNPs conditional on this SNP. Okay, so let's say this SNP explains a lot of the variability of your phenotype, so you'll see a lot of people do a conditional analysis to see if any other SNPs might pop up if you condition on the most significant SNP. So you can easily do that. It's not so easy to do that in R if you have a large data set, but you can easily do that here. Asymptotic empirical p-values you could do. So I'm just giving you a brief overview of some of the functions and features of PLINK. So you could do haplotypic tests. Question?
What programming language does PLINK use?
C. That's right. And so and you can get the code for that as well. That's provided on the website. Yeah. So a number of multi-marker predictors if you wanted to test multiple markers at the same time for association, like a haplotype test for association. You can do that here. You could do some haplotype frequency estimation where it tries to, from genotype data, it can give you estimates of haplotypes. Okay. So it has an algorithm for that. If you have data for copy number variants, so for example, if you have CNVs, then you can analyze that with PLINK as well. Okay. And so gene-based tests, that's going to be covered a little later in this course tomorrow. You can do gene-based tests where you're looking for associations, but looking at all the markers together jointly in association analysis, gene-environment interaction, as well as you're doing like meta-analysis where you want to combine information from across studies. Okay. So what are the input files? Okay. So there's two types. If genotype data is a text file, okay, then there's going to be two files, a .ped and a .mat. So a .ped is similar to the standard linkage format, where the first row is going to be individual ID. The first column is going to be first column is going to be the individual family ID. Second is individual ID. Then the parents, father ID, mother ID, and then the sixth column is sex, and then after that, I think there's phenotype, and then you get the genotype data. But these files are often really, really big. You're talking about like millions of SNPs. Okay, question?
Do you have to know the pedigree in order to use this program?
Well, it assumes you know the pedigree. So for example, if you don't know the pedigree, let's say all the individuals are unrelated to each other, then if you don't have information, then
What if you know they're related, you still don't know how?
then this would not be the program for you. Yes, sir. So if you know, yeah. So, But there are programs for you that we'll talk about, and that's going to be in the session in the afternoon, how to do association testing in samples with structure. Okay, so in your situation, you have structure, but it's unknown structure. It could be like crypto-related pedigree structure, but you may not know it. So there are software programs available for that. So this is more so for unrelated individuals. There are some specialized tests that are available for families, but it does assume that you know the pedigree. So for example, I mentioned here like the TDT, transmission distribution test, where you have like an affected offspring and you have the parents and you try to see which allele gets overly transmitted to affected to try to identify genes that may be associated with the trait. So we can do a TDT test, but you have to know the pedigrees. If you don't know the pedigree or there's cryptic relatedness among individuals, then PLINK is not the software for that type of analysis. But there are a number of software packages that can handle that, and we'll talk about that in the afternoon. Okay, so there's a .ped and a .mat file. So the .ped file, like I said, the first 6 rows are the standard in linkage format. First column is going to be the family ID. Second column is individual ID. Third and fourth column are the IDs of the father and mother, respectively. The fifth column is going to be the sex, and then the sixth column is going to be some phenotype or some dummy phenotype. And then after that, it's just going to be genotype type data, okay, in pairs, right? But like I said, these files get very big. The file that you're downloading are genotype data that's in the .bed format, compressed binary file. Okay? So even a compressed binary file that I'm giving you is like 300 some megabytes. It's over a gig if it's not compressed. Okay, so compression is really useful, and you really want to do that in PLINK because it can read a binary file very fast. If you're trying to give it a PEG file that's a gigabyte trying to read it into memory, it takes a long time. So you always want to compress the file if you can. And then the compressed file is going to be a .bed file. The FAM file is information about the family ID numbers, sex, and the nature. The bin file is information about the SNP. So, for example, what chromosome, the SNP name, the location. Okay. So, and that's the same as the MAP file. The MAP file and the bin file are essentially the same. The MAP file gives you information about each marker, the location of it, and which chromosome and the name. So, the MAP file for this format and the bin file are essentially the same. It's the information about the marker information. But the .ped file gets split into a FAM file and a bed file. So any questions about that? So the map file and the bin file are essentially the same. They give information about the SNP or the markers of interest. Okay, so it gives information about what chromosome is on, what is the name of the marker, what's the location in base pairs or in centimorgans. Okay? The PED file gets split up. So the large genotype data, okay, gets compressed into a .bed file. So all the genotype data in this file gets compressed here. And then the first 6 columns, which gives us information about like the family ID and sex, that goes into the FAM file. Okay, so that's what I think is going to do. Okay. So make sure you don't. You can read. These are going to be text files, so you can view this. Okay. In a regular text editor here, you don't want to open it up. It's going to be a bunch of stars and symbols and things of that nature. I'll try to open it up. All right. So the PED file, okay, pedigree file. This is the first 6 columns are mandatory. So family ID, individual ID, paternal ID, maternal ID. If you don't have information on the paternal ID, maternal ID, then you just put zeros here. Okay, so zeros means we don't have any information about who the mother and father is. So a lot of times you're doing case control studies with, or these large scale population-based studies, you're not going to have information on who's related to parent information and going on. But probably want to get each individual a family ID and individual ID. But family ID, individual ID, paternal, and then sex. X value is 1, 2, and if you don't have any information, any other value seen as 1 and 2 could be in that column. Okay, and then phenotype. So most of the time you might probably want to put a dummy phenotype there because you're going to have a separate phenotype file, which is similar to what we have, where we're going to read it in, right? So you may have a lot of different types of measurements on these individuals. So phenotype file, you can just put -9, which, or some missing number. Just needs some type of just something to fill it in. Okay, so in our case, we have data, phenotype data on two traits, and you can easily read that into R. So it doesn't have to be in the pedigree file. You can just make that a dummy variable. All right. So the map file has 4 columns. So first column is going to be the chromosome, 1 through 22, X, Y, or 0 if unplaced. The RS is SNP identifier. The genetic distance in Morgans. Most of the time, you're probably not going to have information about Morgans. You can just put 0 here and base their position based upon what human genome reference panel you're using. Okay. Based on whatever build. So how do you create? So let's say I have a PLINK file that's myfile.ped. It's a huge file. Okay. And a myfile.map that has the corresponding information as far as like the SNPs in the file. First thing you probably want to do is make a binary file. Okay. So to do that, you're going to use the command PLINK. So PLINK is has a command line program. They also have a glue program too, but we'll use the command line one. So PLINK -- tells us, okay, we want to use the file option. So file, my file. So it's going to look for in your directory a myfile.ped or myfile.map. If it does not find a myfile.ped or myfile.map, it's going to give you an error and it won't continue. It'll say cannot find myfile.ped or myfile.map. Okay? So this -- is the command line option. So the options that you're given PLINK. So PLINK, this says, okay, read in a file called myfile.ped or myfile.map. So without the extension. So it's going to look for these 2 files in your directory. If it's not there, it's going to complain, and then it's going to exit. Question?
What if it's the subfolder in the directory?
Then you need, if you're going to do that, then you need to get the path.
But it doesn't have to have the whole / thing and,
So
/
wherever it is, you need to put the path here. So if it's in your directory, if it's in the same directory where PLINK is, then it's going to look for it there. If it's not in that directory, then you need to specify the path where to find that file. Okay. This right here, this -- make that bed. So this is the option. It's saying, okay, this time PLINK, okay, this is what I want you to do. And if you want information about what this command does, go to the website. The website will give information. But this makes the bed file, and this -- says, okay, what am I going to call this new file? And I'm just going to call it my file. So it's going to create calling myfile.bed, myfile.bed, but without the capital M. It's going to be lowercase m. That's a typo on my part. Okay? So that's how you create the bed file. So that's how I created the bed files that you guys have downloaded. Okay? So any questions about that? Okay. So what are some of the options for data management? Okay? So there's there's a keep. So for example, let's say you have certain individuals that you want to do an analysis on, a subset of people that you want to do analysis on. Okay? You can easily do this by -- keep. So my list.txt could be a list of family IDs and individual IDs of people you want to include in your analysis. Okay? So you can easily do that. Okay? So it would be very difficult in R to kind of subset the data and then try to run the analysis. Here with this option here, you just say just keep or do analysis on this my list of people that you're interested in doing analysis on. Okay. Without having to create a whole new data set with just those individuals. Or you can specify people to remove. Say certain individuals who have bad quality, you just say, I want to remove these individuals. Okay. Let's say you don't want to do analysis on the entire, 100,000 SNPs in your data. You just have a subset of SNPs you want to do analysis on that you're interested in. So you can essentially say extract. So only extract data for these SNPs, and you can also do exclude. You can also just do analysis. Let's say you're interested in doing analysis. Whatever analysis it is, there are tons of analysis. But if you just want to do it on a certain chromosome, -- chrome, CHR, is the option. Question?
For like remove the key, you just put the individual ID, or could you remove the vaccine?
Yeah. So you put this. So you have to tell it which individuals to keep and remove. So you're going to give it the family ID and an individual ID. Yeah. So you just give it a file. So my list.txt is going to be a file where it's going to be the family ID. Let's go, for example. So let's say, this is like, fam 1, person, whatever, 1, 2, 4, 3, and then, I don't know, I 1, 2, 3. So basically, fam and ID, so basically it can be, like, for example, I'm just going to call it MO1 is the fam number, and I want to remove person 1, and MO1, and I want to merge these two. So, for example, you would exclude, you give it a file like this, it's going to exclude individual 1 and family MO1, individual 2 and family MO1. So you got to give it the family ID and the individual ID, and then it'll remove those individuals. If there's no match, then it won't remove anybody. So it's going to look in the .head file or the .fam file if you have compressed the data. Question?
It's very shortcuts to come up with a list of individuals, to exclude, because, if you have like 1,000 observations, are we going to maybe type in manually to come up with a list file, or?
Well, it depends on, there's got to be a reason for you to exclude it, right? So presumably you have some, if you don't exclude anybody, it's going to do analysis with everybody. But presumably there's a reason why you want to look at a subset. So how would you come up with your subset? It's going to be based upon some criteria, right? And so there's some exclusion criteria that we'll talk about. For example, let's say you want to remove individuals who have missing genotype data, more than like 2% of their genotype data missing. You don't even have to do that. There's a command that says just remove those individuals who are missing genotype data. But if you just want to do analysis on a subset of people that may be of interest, presumably you have a list of folks who are subset that you want to include, or if the list of people you want to exclude is smaller, then just do remove. Okay? But you should have an idea on who you want to keep and who you want to remove. Right? Any question? So recoding is often something that's useful as well. So you may want to recode your data. So for example, when we get data, for example, if you get it from like African ancestors, you're going to get like the genotype calls, for example, AA, for example, or for example, you may get something like TA or GG, whatever, how it is. But let's say you want to recode these data into some particular format where you want the data to be in 0, 1s, or 2 format. You can easily do that. Sometimes you get data where 1 corresponds to an A and 2 corresponds to a T and 3 corresponds to a G and 4 corresponds to a C or something like that, right? And so, but you're trying to merge a file that has everything in A's, but you have another file where the nucleotides are coded as 1, 2, 3, and 4. You can easily recode the 1s to A's and 2s to D, and then merge them. Okay, so you can easily do that with the recode option. If you want to change the data into counts based upon the minor allele count, then there's an option called recode A. Any thoughts on why is it recode A? What is the A? By recoding it into 0, 1, 2s. What is that? What would the A stand for? What kind of model is it? It's like an additive model, right? So basically, recoding as an additive model. So I also said that you can read in files. Okay, that have phenotype information. And that's what you're going to do with the two phenotypes that we're going to analyze, transferrin and height. Okay? You can read it in with -- pheno, for example. And then you can also give it a file that contains multiple phenotypes as well. And you can let PLINK know with an option. I can't remember the code, but you can look it up. Where let's say you have a whole bunch of phenotypes, you have a whole different measure like height, weight, BMI, systolic blood pressure, and then if you just want to extract or do analysis on a couple of the phenotypes, then you can, with this option, you can choose which phenotypes to analyze. Okay, with this one, you analyze all of them. Okay, so there are a lot of different options here. Okay. So what about quality control? So, we said that if you're trying to do single variant association tests, you probably want to exclude very rare SNPs. So, single variant association testing with SNPs where only 1 or 2 people have it, okay, there's no power there. Okay, so you got to use other techniques, which Mike is going to talk about in more detail tomorrow. So you might want to exclude it based upon minor low frequency. So, for example, in the GWAS you're going to conduct, for example, I'm asking you to exclude SNPs with minor low frequency less than 0.05, but you can choose your threshold. Okay. If you want to exclude SNPs that have high missing rates, you just use -- geno and then you specify some number. For example, if you want to exclude SNPs that have more than 1% of the values that are missing, then you would use -- geno 0.01. And then you can exclude the individuals who are missing individual, or you can exclude based on Hardy-Weinberg. So those SNPs that are out of Hardy-Weinberg and deviate substantially from Hardy-Weinberg, you specify the threshold for that. You can also easily calculate individual summary statistics, the minor low frequency of the SNPs, SNP missing rates, individual rates, and as well as Hardy-Weinberg. So you can easily do that. So you can get summary statistics where it prints all this information out for each SNP or each individual. And here, this is what you use to do quality control to exclude individuals from the analysis based upon missingness, or minor low frequency, or an individual missing rate, or Hardy-Weinberg. Question?
So you mentioned, like with the low minor or low frequency, by putting -- geno 0.01, you don't need to specify anything else. It'll go through your total data set.
Yes. So -- geno 0.01 is based upon missingness. So those SNPs that have more than 1% of the genotype cause missing, it's going to exclude those SNPs from the analysis. You don't have to do it automatically. Okay. Minor low frequency is going to exclude those SNPs with allele frequencies that are less than some threshold. So this is based on allele frequencies of those that are genotyped. If the allele frequency, minor low frequency is less than some value, let's say 0.05, it's not going to include that in the analysis. It's going to exclude that from analysis. This is about missingness. If there's a lot of SNPs, if there's a SNP that has a lot of missing data, then that SNP is going to be excluded based upon the criteria that you specify here. Okay, if it's not satisfied, then it's going to exclude it from the analysis. Questions?
So as far as excluding SNPs that are in LD with GWAS data, do you need to do that with exome data since it's the actual SNP and not the marker? Does that make sense?
Yeah. So what's the goal? So are you worried about LD? If you're worried about LD,
should I be?
Yeah, why not?
Well, because
I mean, what do you worry? I mean, there's going to be LD and exome SNP
yeah.
data as well.
So I should also
Why?
do the threshold.
Why? I mean, what are you
Because
trying
then
to do with it?
they're dependent, I guess.
Yeah, but you can still do the analysis and then just decide which ones to include, right? So there's ways to measure LD,
Right.
So there are tools here to determine which SNPs to include based upon LD.
I'm just wondering I know you should do that for GWAS data, but I wasn't sure if you should do that for
Yeah.
exome data.
But exome chip data is correlated, right?
Yeah.
Yeah.
So you should still.
Yes. So if you want to do an association analysis, so let's say we have our quality control thresholds and we specify that. Now we can do association analysis using the following options. So that's association, you're going to do an association analysis. This says association with quantity trade, but this actually does everything. So dash is, if you give it a phenotype type file, it's actually going to look and see whether or not it is a binary outcome or a quantity outcome. So this actually comes as this. I mean, so even if you do this and you give it binary data, it's going to recognize that, oh, it's a binary data, let me do a logistic regression. If it's recognized quantitative data, it's going to do linear regression. Okay. So you can do stratified analysis if you want to just do analysis within clusters. Nice feature here is that you can easily add covariates. So let's say you want to adjust in your linear regression, logistic regression model for age, sex, BMI, or race, or some things that may be important to your outcome. You just provided a file with the individual family ID, individual ID, and then covariates, and then you can specify what covariates to adjust for in the model. Okay. So this is just some of the features. They have a whole website dedicated to a lot of the features. So go look it up. Okay. So let's talk about the GWAS that we're going to be doing. So we're going to do a GWAS of transferrin. So that's an iron deficiency related phenotype. Question first.
For instance, the way R can handle, I mean, you can have more than one object at a time in R. Can you have more than one, like, data to analyze in PLINK, like make reference to different data set at a point, or you have to work on the data processing?
Yeah. So most of the time, so for example, you can, so it's going to be one data set at a time. Okay. So PLINK, for example, let's say you have two data sets, you can merge them using the vmerge or merge command, and then make one data set. But you can't read in multiple data sets at the same time. So these are our input files, transferrin.bed, .fam, .bim. And so there's an R script that I provided, and also some PLINK commands. And so, but also it said, use the PLINK website as well. Okay? So use the PLINK website as well for your questions. So let's think of some of the things that we could do. We can answer. Okay. And we're actually going to be using PLINK and R to analyze this data. So the first thing is copy or download from the memory sticks the PLINK files. And we're going to first use the R script to inspect the files, but don't read in the .bed file. So we're just going to read in the .bim file and the .fam file. Okay. So certain questions you can look at or answer how many individuals are in there, how many SNPs are there, is the transferrin phenotype approximately normally distributed. So we can look at that. Okay. And then, for example, we can estimate the low frequencies at all SNPs. So this is the command that you can use. So if you have a MAC, you may want to use the period, let it know where the directory is. Some MACs work, some MACs don't. Some MACs don't need it. Mine does. So I need to specify that PLINK is in this directory here that we're in currently. So you may or may not need the period and // if you have a MAC. So calculate SNP and individual missingness. You can use these options for each SNP. You can obtain p-values for Hardy-Weinberg equilibrium. You can use the following options. So this here, that's just Hardy, and then this is saved into some alpha file randoms for Hardy. So you're going to run a GWAS analysis of transferrin, and so you're going to apply some quality controls. Question? Oh, okay, I'll get that afterwards. Yeah. Does anybody else has everyone downloaded the data? Okay, great. Thank you. So we're going to apply some quality control. So you're going to apply quality control to the minor frequency, missingness, Hardy-Weinberg equilibrium. And so this is one of the commands that you can use. Okay. So as I mentioned, you can easily analyze a subset of SNPs. So if we have a following file that has a list of RS numbers, SNP ID numbers, SNP list.txt, you can use following SNP commands to just do the association analysis on a subset of SNPs. Someone mentioned about R squared. Let's say you want to know how correlated are your SNPs. Okay. You can easily just use the R squared command. So that is a measure of the LD. And so that's R2. So essentially what I'm saying here, read in this transfer file, extract SNP, only these SNPs. So this, we're doing analysis on this subset of SNPs that we're going to provide. And then do R squared, calculate the LD for all pairs in this file. So if I'm not mistaken, I forgot where the threshold is, but I think if the R squared is less than 0.4, it doesn't report it. It only reports, but you can change that threshold, but you can look at the manual for that. So this is the paper that introduced PLINK, but they've added a lot of features since 2007. As you saw the latest update was in May of this year. Okay. Question in the back. Yes, so there are differences. So the newer versions, they have more options, and they're faster too. So they're I forgot what version it was. Where I think I have version 1.07. I think I haven't tested the new version, but there was a huge difference between 1.07, I think, and the previous version. All right, as far as speed. Okay, without further ado, let's. Some of the exercises. And then we'll go over just some of the basics. So first thing, you guys can't see this very well. Is there a way to increase it? I don't know. Okay. So on the website, there's some basic commands, basic R script. Let me see. Okay. So for session 3, so there's a PLINK script file, for example, once you do the association analysis. But the first thing you probably will want to do is to do the R script first. So the R script is useful because it allows you to kind of read in the data, look at the number of individuals, so they answer the first few questions. So once you have some idea about the data, the first thing you want to read in data, so you see what the data is about, how many SNPs there are. Then after there, then you might want to read it into PLINK. Okay? So one of the first things you may want to do is to, for example, calculate allele frequencies. So let's use PLINK to calculate allele frequency of the SNPs. Okay. So I can use this command PLINK. Transferrin pheno. We don't even need this because the calculated frequency is not going to need any phenotypic information, and then dash it out, dash TR. So if it doesn't need an option for the analysis, it's not going to use it. So here, I'm going to control copy. Okay. So now, can everyone see that? So now it's running this command, it's getting allele frequencies for every step. So as soon as you run it, it's getting information, right? It says reading the map file. There are 281,013 markers. There are 4,861 individuals. Okay? And then this is genotype data value, and so it just gives information how many males, how many females there are, and then reading that, and then detect it. So it's read it in, and so there's some information as far as like what analysis, and these are the options that are in effect. That's the file, and out. So now it's going to be calculating the allele frequencies. That's the wrong one. Sorry. I don't even know what this is. So for the allele frequency, I think the option, what's the option for frequency? Is it dash freak? Freak, yeah. Okay, so I need to add the dash freak option. Okay. Is it FRQ? Is that right?
FREQ.
Okay, thank you. Okay, so let me redo this. Okay. It's standardized. Okay. Yeah, it's standardized. Yeah, so it's a standardized height. Yeah, or height has been adjusted for something. Yeah. Okay. Good question. Yeah, exactly. Yes, it's been standardized. Maybe the mean of all, the mean for men or something. I'm not certain yet. Okay, so the output of when I do the frequency is tr.freq, and so you can open it in a text editor, or in this case, since I'm using a Windows machine, I can actually use the more command, M-O-R-E, tr.freq. Okay, so for example, so this is a file that gives me all the little frequencies, minor frequencies for each marker. So it's chromosome 1, SNP name. A1 is the minor allele, A2 is the major allele, so the minor allele is a T, the major allele is a C, gives you a frequency, and then these are the number of chromosomes, the number of alleles that are used to calculate the alleles of the frequency. Okay. So you can do all types of different options. So if you wanted to do the association analysis, okay, with transferrin, so here we're going to specify the tr.pheno, which is our information for transferrin. And if you want to see what that looks like, more tr.pheno. Okay, so this is a transfer phenotype. So this is information on transferrin. So it has individual, family ID, individual ID, and then these are the values. So what does NA mean here? This is data, no information, right? No phenotype.
This file you're using, that doesn't look like the one I'm
Yeah, it's my file, but you have the data. You have this command in there for association analysis, right? It's not the same file that you have, but it's the same commands, right? All right. So in this analysis, I'm doing association analysis with this phenotype using minor frequency cutoff of 0.05, phenotype missing of 0.01 for SNPs, heart of 0.01. So reject or exclude all SNPs that have heart of equilibrium p-values of less than 0.01, and then do the association analysis. All right. So I'm going to run this. Okay. So does anybody have any problems or anything? You're running fine. So first use R, read it in, look at the data, then you're going to go to PLINK, and you're going to run the association analysis, and then it's going to create some output files, and then you're going to take those output files using the R script that I gave you, read in those output files, and then we're going to do some nice GWAS and Manhattan plots. That data.
They have a section that looks like why do you make this event? It's like, it's not that like, I don't mind it because
Yeah, I've been checking. There I am. So you're if you can't, no worries. There's another. So some people have a problem with bioconductor. If you don't, there may be some problems with your system. But there's, I gave you another software package that you can use man. So you can use that to do the block. You can't do bioconductor.
No, I need to say
You don't have that. There's another harness in that section. So this you're going to create that. Yeah, you're going to create it just two, but I gave it to you. So you're going to go to R. You're going to read in all the data. So it's not like well, and then to like find it, so wherever you have Okay, just snip maybe are the most significant, extract it out, and just create a text file with the snippet and call it snippet. Yeah. Does that make sense? Yeah.
Yeah, no, sometimes it can be very, very frustrating. But yeah, I mean, that's so we used to do these reasonable code predictions. Yeah, certainly. Okay, I'm the only user. Okay, I'm gonna make something. I did, but it's a couple.
So basically, saying check something. So I just did like, you see so I just took our file transfer and it just said only the ones that binary affect the cycle. And then you do a read code and then out snippets text, and that'll take a subset that has binary frequency
Okay.
and put it into a separate text. And then I think
Okay.
does that make sense?
Yeah, so you made an arbitrary subset.
Yeah, because I was looking back at the other subset. He only used 10 variables. I mean, maybe you should use something greater than 25 because
Okay, so it's dot, what is dot AF?
it's dash
Yeah.
space 0.05. That's just what we're using.
We're using the
Dash reset. Yeah, so it's just that. So it's PLINK --v file Transferrin.
Okay. So what you did is you're sending
And then the
just to run what you would run in terminal. So it can see. So you did that, but there's
I had two years.
if they're an LD. If they are, you're only going to record one of them. Yeah. Otherwise, this is especially interesting.
Because so if they're in LD, they're basically all associated.
Right. So there's so I don't know how to do that anymore. But you always want to have
So we have about 5 minutes left. Was everyone able to get it running? Question?
I'm still wondering, like, how do you obtain the top 10 most significant SNPs and then extract those SNPs?
So just copy and paste into a text file.
Yeah, but how do you? Oh, so, but how do you get the top 10?
So that was you know what? Okay, so we could go over that real quickly. So everyone is able to run the PLINK analysis. Okay, good. All right. So now. Okay. All right. So. Okay. So. So just following the commands that I provided. Okay. So we have some information about the transferrin phenotype. 4,861 individuals. And, okay, you want information about the number of SNPs, that's the map information. Okay, so there are 281,313 SNPs, okay? So that's information. You can do some nice plots just to look at the distribution of transferrin. Okay. Oh, sorry. All right. So approximately normally just distributed, and you can do the same thing for height. So someone mentioned that height was negative for some individuals, and that's because it's a standardized height value. Okay. So it's been normalized, standardized. Okay. So after you run your PLINK analysis, and you've uploaded or installed GWAS tools, and if you wanted to know something about the GWAS tools, then there's vignettes for it. But here's information for, I'm reading the data file that I created using PLINK. This is the output for the association analysis. And if I wanted to just to look at the results, I ran PLINK, did the association analysis, and now it's giving me all the associations. So I have chromosome SNP, base pairs, non-missing, people who don't have missing genotype data. These are the people who we use for this SNP that have non-missing genotype data. This is the beta in the linear regression, standard error. This is the R squared for the linear regression. This is the t statistic, and this is the p-value. So this last column is the p-value, the association p-value. Okay? So any questions about that? Okay. So there's, if you wanted to plot, do an association, a Manhattan plot using GWAS tools, use the Manhattan plot function, and it's going to give you all the p-values by chromosome. So if you wanted to, okay, if you want to just do a plot just for the autosomes, you want to exclude the X chromosome and the mitochondrial and the other non-autosomes, then you can do a Manhattan plot for that. Okay. So you could see something like this where it just goes up to 22 now. All right. So you can obtain a QQ plot, which kind of tells you about the assumptions as far as whether or not it well behaved. This is what behavior. You do see some deviation. This is what you expect under the null, but you see there is some slight deviation off of them. So there may be some issues with calibration. There may be some cryptic relatedness or population structure we talked about that you may want to adjust for in this analysis. Okay, because you do see some slight deviation from it. So if you looked at the association plot for the Manhattan, nothing was significant at the genome-wide significance level. Now, what about if we did same analysis, but now for transferrin, same. So now I'm going to read in the transferrin association results from my PLINK analysis. Okay. And so, head. Okay. So now let's do a Manhattan plot of transferrin. And what do we see here? We have two genome-wide significant regions. So one on chromosome 3 and one on chromosome, is that 6? Is that right? Okay. So you really can't see this diagram, which means that it's highly significant, it's regular significance. And so if you wanted to see exactly where it is, you can increase the y-axis. Okay, that's what I'm doing here. So I'm trying to figure out Manhattan plot. So these are the two genomes, so highly significant associations. So you can also do a QQ plot of that as well. Question was, for example, how to identify the top SNPs for transferrin. Okay, so what would we do? We would just, for example, the top ones, we would just order. We're going to order the transfer data set based upon p-values. Smallest goes first. So this is what I'm doing here. I'm reordering the data set where the smallest p-values are going first. So here, and then, so these would be my top most significant SNPs because I reordered the data based upon the p-values. Okay? So if you wanted to look at the LD, you just create a file, a text file with just the SNP names.
So you can't, in our, tell it to make a file. with just-
You can extract it and print it out. Yeah. So so you can extract it. You can tell R to give me the top dollar sign SNP, and then you can print that out for the file as well. So so then you can do that as well. All right. So if you look at the top SNPs and top regions here, if you look at on the course website, I provided an article where you can look up results as well. So this article here, if you're interested in, this is similar data from this article where they did a GWAS, and lo and behold, this is what they found to the same. So this is the same data, okay, but for Transferrin. So if you're interested in comparing the results from your analysis to what they did, which is basically similar, you see that you're getting the same genome-wide significant hits using this data. Okay, so that's your GWAS with PLINK, fast and efficient, thousands of individuals, 100,000 SNPs. You did it on your laptop in just a few minutes. Okay. So with that, I'll stick around. We have a break right now. If you have any questions, have any printed problems, I'll be here during the break. And if not, see you back in 25 to 30 minutes. Thanks.